Hello, everyone. Hope you can hear me. I'm Naresh Mehta. I work as a solutions architect with NVIDIA. And today I'm going to talk about ASILs and ASPICE, safety. You know, I mainly work with automotive, so when I say safety, should be understood in the automotive context. It is applicable for everything else, aviation, yeah, any kind of automotive, but this would be more specific to vehicles as such. A disclaimer, everything that I show today, I talk, is in my own capacity as an open source contributor, so take it like that. There were two parts of this presentation. The first part was to understand what ASIL and ASPICE is. The second part was to understand how we could accelerate Linux component adaptation in automotive industry. The second part, though, will take a long time and would be discussed quite in detail in the coming 2 weeks in the ELISA workshop hosted by Volvo. So we will have some discussions if time permits, but not a basic content today. So what is safety? Anybody? No. So safety is to make sure that things work as expected, and we know when it is not going to work as expected. And we take measures to make sure that those kind of unexpected situations don't occur. Basically, safety is elimination of unknown. Just to give you some examples, in 2000 and I think it was 8 or 9, 7 or 8 somewhere, Toyota had unintended acceleration in their vehicles. Basically, the user was not pressing on the accelerator, but the vehicle was still running at full speed. There were a couple of fatalities there. There were a lot of recalls. Toyota had to end up paying millions of dollars in settlements. Another safety example would be the Boeing MAX. It had safety mishaps since it was launched. A lot of different cases there. Some of them were because the safety culture was not followed. We'll talk more about the details of safety culture. Some of those things were because of misunderstandings and interpretation of the safety requirements. But before we go into more details, I would like to go through the agenda. So what we'll do is, we'll go through some acronyms. We'll talk a little bit about functional safety, risk and risk assessments, how it turns and modifies itself into an ASIL level for a particular component, what does the standard say, and then we have a complementary software process improvement and capability determination model that works and is a complement to the ISO 26262 standards. So something which is very different when it comes to software development and how it should be approached in the context of safety. Raise questions as and when you want. We'll not wait till the end for taking questions. So I want it to be more interactive. So these are like, 1% of the acronyms used in safety. If I list everything, there would be like 40 plus slides. The ISO 26262 specifications, this is a huge specification. It's 12-part specification, goes right from defining the terms. Terms are different, but these are the acronyms, terms. It defines things like hazards, failures, risk, etc. So to make this more interesting, whenever we talk about automation in the automotive industry, you all would have heard of the paradoxical situation where a car is approaching full speed, brakes fail, you have a crowd standing to the right, there is an old woman crossing the road in the center, and then on the left, there is a wall. And now, there's a moral and ethical question. I mean, these have been addressed in detail if you read let's say, critical interpretations of safety and ethical considerations of automation. Then the question is, now that the brakes have failed, what should happen? What will a human do in this case? And what a computer will do, or our automatic system will do. So depending on which side of the scale you are, you might end up hitting the old woman. That's the least possible damage. You might end up killing yourself, morally correct. Hopefully you'll never drive into the crowd. If you are thinking of that, get yourself checked. No, kidding, kidding. But then, when you have that answer in a moral ethical consideration, you also have another variable added to the equation where you have kids in the back. So if you're thinking the first answer, that probably is not the right one either. So what do you end up with? No, you don't. When you have done your automation and safety according to the specifications, you have followed the process, you have discovered the unknowns, you have applied your risk reduction strategy, that particular situation will never occur. The car will know that this thing is happening, there is crowded space, I am losing control, it will have alternate measures to not end up in that situation at all. So hopefully when I was talking there, you would have read this. We'll come to this parts of this later. The most important one are ASPICE. As I said, this is a software process improvement and capability determination model on an organizational level. Gives a lot of processes from different perspectives, from the inception phase of the product, when you just start thinking about it, all the way till you decommission the product. Then you have the ASIL, Automotive Safety Integrity Levels. These are also defined. So there is a process on how, which component should have which ASIL when you use it in a car. You cannot have everything at the highest ASIL. One of the important things to remember is that whenever you have a component which has to be applied or let's say you have to apply an ASIL level to it, the cost for that component increases. So if you have a QM component, for instance, or the lowest is QM, I would say highest is D. If you have a D, your software development cost increases by roughly 60 to 80%. In a normal situation, it can go beyond that. HARA is a very important, much needed step when you talk about safety in automotive. So that's the hazard analysis and risk assessment. It will give multiple outputs, mainly risk, and then you have risk reduction strategies. All the things, the ETAs, DFAs, FSC, TSC, etc., these are all risk reduction. Another important concept is the safety element out of context, so SEOC. Generally, when we talk safety, when vendors provide you certain components labeled as ASIL B or ASIL D or ASIL C, whatever, they have certain assumptions with regards to the working environment for that component. So once you go out of the bounds of that assumption, you don't follow the restrictions or the recommendations that they are providing, the safety is thrown out of context. It's gone. There's no more safety. Then we have the fault detection. Very important aspect on how, what is the time period when a fault is detected, how soon can we react, handle the fault, and how soon, or what is the maximum tolerance time that we have in our use cases. So we'll come to parts of this in the coming slides. You see, what is functional safety? So as I said, safety is the absence of unreasonable risk, and ISO 26262 goes into details of defining what reasonable risk and unreasonable risk is. But unreasonable risk is something that results into fatalities, uncontrollable situations, which can cause harm. EPE systems are electrical, electronic, and programmable electric systems, basically everything computers. If you want to launch an automotive, you have to follow the 26262 specifications. Of course, there are countries where this is not followed, but then they're not safe behavior on roads. There are many examples. You have heard of Tesla's, the FSD module, etc. And there are quite a few accidents that have happened because of not following the specifications or doing development in a different way. So as I was saying, this is what the ISO 26262 in general is, or it's still part. But it starts with your management of the functional safety, you do that right from the concept phase itself. So let's say as a vehicle manufacturer, you decide, oh, I want to have an L2 plus vehicle, L3 vehicle, whatever vehicle on the road. So you have to start the process at the beginning itself. You have to do the safety lifecycle initialization. The hazard has to be carried out before even you think about buying wheels or steering for your product. The software development is part 6 in the product development. It's a very small box in this big space. But that's where let's say, main emphasis for safety would be. Hardware, of course, is hardware has its own safety. So software is as safe as the hardware is. The hardware has to be certified to work in certain conditions. And once that has been done, the software has to build on top of that. This goes on from the concept phase up to the decommissioning phase. So even if you have sold the car, you do software updates on the car. I mean, all of you are aware that people have been talking about software-driven cars. And what are they? That means that you can change and control the features of the vehicle through software at runtime, when it is stationary, as needed. Most of the functions, there are multiple levels of automation, right from L0 to L5. We are kind of targeting L2 plus L3 conditions. There are some, let's say, manufacturers targeting L4 as well. But there will be time when we reach there. So what do we do in functional safety? We make sure that there is no unreasonable risk. There is no unknown. We know where the failure is, even if there is a failure. Sometimes people think of safety as something which can never fail. That thinking is wrong. They also think of safety as something that should have no bugs. That understanding is wrong as well. I mean, it should have no bugs, but if you have a bug, it doesn't mean it's a... As long as you have planned for handling that.
Should be defined behavior, right? What
should
happens?
be defined behavior, deterministic behavior in any situation. So there are ways of let's say, doing this, determining unreasonable risk and reducing it. One philosophy that ISO 26262 goes with is the risk reduction. So you avoid systematic faults. Systematic faults is something that is always reproduced. So if you have a function which takes an int 8 as an input, if you're going to exceed the int 8 boundaries, you'll be doing wrapping and going into negative or let's say undesired behavior. So you avoid that, you control the systematic faults so that it doesn't occur. And then there are something known as transient faults or random faults. And these are something that cannot be really tested in your test setup, in your vehicles. But when you do your analysis, you know that these things will fail. And you have to have strategies to handle those transient failures. The safety goals are something that comes as an output of HARA. So based on the safety goals, you define how your vehicle should react in certain situations. What are the safety concepts that you should adhere to? And from that, you derive your safety requirements. And then, and that's the start of your software development process. And then, of course, from a hardware perspective, you will have safety integrity mechanisms built into the hardware to make sure that you can provide for a proper software. Oh, I'm pressing the wrong button now. Okay, so we have been talking about risk and risk reduction. So risk is the combination of the probability of occurrence of harm and the severity of that harm. So there is risk everywhere. Whenever a vehicle moves, there is a risk. The risk can be categorized as two major cases. One would be the acceptable case, and then we have the unacceptable case. So there are certain risks that we have to kind of accept. If the vehicle is moving, there is a risk. The wheels can fall off, the tires can explode, steering wheel can go. So when you do your HARA, you define the end user risk, and some of the examples that I gave was, if you have a wheel which is, let's say, filled up with more air than it should be, the pressure is too high, it can blow up. How do you bring it down? So you apply your risk reduction strategies. You define mechanisms on how to do it. So then you first document this, that this wheel should not have more than 20 psi or 30 psi, whatever, tire pressure. Okay, yeah, that's a documentation that brings down risk, but it still might not fall in the acceptable range. Then you have alternate mechanisms. You have preventive measures. You implement TPMS, tire pressure monitoring system. So then you can, basically the car can know, okay, you have more pressure there, less pressure there, blah, blah, whatever. So that's preventive. Then you have corrective functional safety functions as well. So you basically might have software which says, if the pressure is above 30 psi, which is maximum of safe operational range, your car will refuse to move. Even if you keep on pressing the accelerator, nothing will happen. So it's not that everybody does this, but these are some of the risk, let's say, risk mitigation measures that you can have to bring down the risk to acceptable levels. So then we come into the ISO part of what ASIL do you define your components. And as you can see, ASIL D is for components where the risk is very high, the probability of occurrence is very high, and the severity of harm is very high. So in components where you have or you want ASIL D, you should not have failures. The component should always work as expected. And one of the examples of such a component would be airbags in your car. The airbags are not deployed every day. They are rarely deployed if in a, let's say, life cycle of the car. But when they have to be deployed, they should deploy. Failures are unacceptable in that case, because if they don't, the x-axis, the severity of harm increases hugely. So that's why either you bring the probability of occurrence down, it should always deploy. There is no way it could not deploy. If it fails to deploy, you still have preventive measures. So you have a ASIL D specification there to comply to. An ASIL is basically exposure times controllability times severity. So the more exposure you have, the more severity you have, and the less controllability you have, the more higher level ASILs you will have. Another view of the same diagram. So these are the kind of component analysis that typically needs to be done in automotive when you are defining levels for your components that you are going to use in the vehicle. You have the lowest severity where there are no injuries, then you have some higher severity. You can define how many classes you want. It doesn't have to be S1, S2, S3. You can go more granular in that sense. Similarly, on the exposure levels and then the controllability aspect. But one thing to notice is that when you have less severity, when you have more controllability, and the probability is less, you can do away with QM components, so the lowest levels of ASILs. If you look at that, ASIL D, the highest component level there's only one box which kind of goes there all the way, which is where you have no controllability, more severity, and more probability of occurrence. So, before we go there, I wanted to say one thing. Your components alone do not make your car safe. So let's say if you have an ASIL D component, for instance, which is used in a system context in an incorrect way, then there are possibilities of harm, let's say hazards, hazardous situations. If you look at one of the examples, I watch a lot of this FAA stuff, you know, the Federal Aviation's investigation, and one of the examples was they had redundancy in their system. So they had altitude measurement sensors located outside the aircraft. There were 3 of those. And then they were for redundancy. So one is enough to give you the altitude information. But by luck, the one that was going to the computer was covered with a cover which the maintenance crew forgot to remove. Now that computer was giving faulty readings, or that computer was receiving faulty readings, and there was another on the co-pilot side, which was the actual faulty one. So now what happened was that in the situation where they were up in the air and that it was nighttime, you know, they could not really see where the horizon was. It was very difficult for them to understand what altitude they were on. So they asked the computer, they did some calculations, checksums that were there in the manual, arrived at the long conclusion that the faulty one, the right side one was the right one, rest 2 were faulty, and then a mishap happened. So things will be like that. So you need to make sure that your operating environment, the assumptions that you have, and that brings me back to one of the questions we had in the previous one, right? Why do you need static arrays, or why do you need arrays on stack? Memory allocations and deallocations in safety are not looked at with respect. So it has to be deterministic. If your task has to be executed according to certain duty cycles, it has to be executed. You cannot skip it. There's no way you can skip it. If you do that, your safety assumptions go off the track. So, yeah, let's talk a little bit about standards here. For the ISO 26262, as I said, it has requirements on organizations, processes, and methods. You cannot just develop a software component based on, oh, this looks good, this is optimized, you know. I have, and I think one of the presenters showed a big C function as well, compressed, thousands of lines of code, complex behavior, threads everywhere. No, that's not something that is looked good by the standard. So standard says, make it simple. The more simpler it is, the better it is from a safety perspective, because you would be easily finding the errors, the non-functioning cases. It covers the whole of the product life cycle, as I said, from concept to the decommissioning phase. So as long as the car is on the road, those standards apply. Once it's, even there are standards for decommissioning it, so you cannot just go and dump it in the recycle bin. It defines guidelines in order to comply with different safety levels. So we went through the safety levels before. There has to be evidence of safety case. Everything is evidence-based. So I cannot go and say, hey, you know, I have tested this. It works on thousands of machines, and so it's safe. It works on this machine as well. No, that argumentation, that point of argumentation is invalid. There are multiple reasons for this, because the test or the environments that these are run in might be very different than what it is actually running in for that evidence. So the evidence of safety case has to be from requirements, architecture, design, all the way to verification. We'll come to the verification is an important part. And of course, traceability. We have to have traceability. There should be nothing that is not desired in your code base. So if you have dead code, if you have code which is not executed during your test, etc., you need to make sure that either you remove it or you have the reasons to have that code base there. Everything boils down to a good safety culture from an organization perspective. So I had a lot of team members. When safety was introduced first in the organization, people were not able to understand why we want to do this. We have been writing amazing software. Everything is working. It's running on thousands of machines. we have documented source code, so we have Doxygens there. And why do we need more documentation? Why do we need to elaborate on the requirements? Why do we need to write an architecture which is already in use? It's working fine. Many people thought safety is more documentation work. No, it's not. Documentation doesn't make things safe. Documentation is a part of safety because it gives you the evidence and the traceability for your safety case. In a good safety culture, safety is regarded the highest priority. So let's say you have to make a decision where you want to do things faster, you want to have a safe way of execution, then obviously your choice should be safe way of execution, not the faster way. Safe way might be slower way. No. And then of course, you do continuous process improvements. There is a proactive attitude towards safety. So when you start thinking of a new feature, I want feature X in my source, in my component that I'm developing, then you think about what that feature X will do. That's a good thing. And then you also think about what happens if that feature X fails, if anything from that feature fails. We had some presentation of bugs in the kernel, etc. These are the things that we think about. I mean, when things go right, everything is good. But when things go wrong, how do you do that? There are certain things that your component might not be able to solve. So in that case, you have to document it, that this particular component, if it fails, it will fail, it will have this drastic impact. There has to be some other entity who has to solve it. And then, of course, you should be aware of what your components is being used in. You cannot just have a generic component. I cannot have a camera and say, hey, you can use this for automated driving. You can also use it for driver monitoring. You can use it for, let's say, adaptive cruise control as well. That's never going to work. It has to be function specific.
Right. Just interrupt a little bit. Do we have like 10 minutes left. Should we try to get a discussion going a little bit?
Yeah.
In the end, do you have something like?
I just have a last slide.
Okay.
And I can quickly go through this. So this is the model that I have been talking about. We don't need to go into the details, but here, a lot of emphasis is on the middle V, the red box. As I said, it goes all the way from requirements to qualification tests, both on the component level and on the system level. And the box is important because it defines your boundaries on what things you want to do and not do. And this also establishes best practices that any organization committed to safety should follow. So personally, I would say that if we already have checklists and guidelines on how to, let's say, push patches, for instance, or how to write our code and what checkers to run, etc. It would be good if we as open source community can come out with best practices, not best practices, best practices that everybody must follow. How we define the traceability aspect. Yeah. And now I'm open to come.
Yeah. Thank you.
Thank you. So, this last thing, my GitHub. I'm mostly into custom ROMs. You can find me on XDA. I have stopped doing that now, though. So, but there are some important, nice things there. And then I have a personal website, some weird articles that you might find useful.
Okay.
Okay.
Thanks.
Thank you.
So, I mean, the ISO standard is essentially a document, right?
It's a standard.
It's a standard, yeah. So it's also like you describe it. It's a philosophy. It's a way of developing stuff, right?
Yes.
But it defines everything in a very specific way, right?
So
you need to follow procedures. You need to do this and this and that. And in the end, you get like a stamp saying that, yeah, we did it.
No. It's not that easy. There is one part that I didn't mention. So even if you, let's say, follow ISO 26262 all the way, there's an assessment that happens afterwards.
But how good? I mean, there's no guarantee that things are safe just because there's a document, right?
No. That's why there is an assessment. And there are usually independent assessments for the components that you develop. So let's say I develop a component. It's not me, myself, doing the assessment and certifying that. It's usually a third party who doesn't know anything about the component, which does the assessment. And the way they do the assessment is, it's both a technical assessment, but it's also a process assessment and a traceability assessment. So you should be able to prove your case all the way through before you get a certification.
And then you don't change anything after that.
And then you don't, exactly. So whenever you develop a component, you develop it in a box. If one thing changes in the box, it's invalid. You have to go through the
you can't
change request process. Sorry.
How do you do security updates for your Linux?
You have to do SIAs. So whenever a new thing comes up, let's say a security vulnerability has been found in your code, you start analyzing, you see what portion of the code is affected, then you do a reverse, let's say upwards traceability as to what will change because of change or fix in that particular code. And that's your safety impact analysis, SIA. So this SIA has to go through, there are other components in the organization like a safety review board, for instance. They'll then say, okay, this is okay to implement. This is a high priority security fix, low priority security fix. There's a lot of impact analysis done before you even start touching the code. And once you have done that, you again follow through the test procedures, make sure you have not broken anything else by fixing that.
Is that feasible for security updates for the kernel, for example? Can you do all of that in time?
That's a good question, and I think we'll have discussions in the ELISA for that. But
sorry. Yeah, I shouldn't hog this. Sorry.
Hi. Since I've been dabbling in safety critical development since the 90s, when I took a class for Nancy Leveson in Safeware, and I'm bit familiar with regulatory things. Regulations is part of constraints, and any artist, any creative person, because we all like to think as developers that we're creative. If you don't have any constraints, you can't be creative, you can't be innovative. Use the constraints as an opportunity to define, much like you can make much of a drawing by just drawing the shadows. It is an opportunity for creativity, it's not a threat. That's one thing. On the other hand, and one of the 3 OEMs in Sweden, I listened to some hopeful CTO in one of the outlandish subsidiaries of that company that hope to replace all proper engineering in my take, proper engineering, in certain key safety critical things with AI. Not even generated, but so that you could verify, but you could hand over all safety critical things to the AI because it would be better. And I don't think so. And I still hope that this guy will have a great opportunity to pursue that in something that I don't drive.
You can be heated by it?
Sorry?
You can be heated by it anyway.
Not if I see it first.
Someone put it on the street.
Yeah.
Hello. Many teams work following the agile methodology. Agile methodology is more interactive, like you have many in a loop, like you can have new inputs, outputs, and the SPICE, it's more like the model is waterfall. And do you think it's possible to adapt the agile methodology, how the teams are working, into the ASPICE? And
Yes.
I already heard like some people saying, okay, we can have these small V's inside in the agile, but it will reflect the real how we are developing software, or it was just something that okay, we are presenting like this, but we are doing like that.
Yeah, it's a good question. So I'll tell you what I follow in my teams. And what we do is we do the small V's iteratively and incrementally. So we don't do this waterfall right from the start to the end, even though the process says it like that, because anything that changes at the requirements level has an ultimate impact on the assumption box that you have created for your component.
But in this case, for example, you have all the traceability requirements and the other things that you already had documented. It will not be easy to update these stuffs, like when you have like a new loop or a new interaction in your process.
So there are when you start with this process development, you have certain milestones that you define. After a certain milestone, changes are, I wouldn't say not possible, I would say they are harder to get in. You have to follow a change request process. So there are, you can define the milestones in a way you want. So we have a planning milestone, and then we have an architectural design milestone, then we have a verification milestone. So anything coming after architecture and architecture and design milestone is pretty hard to get in, because we have already decided how to go ahead and implement the software component.
Okay, but also these new interactions needed to be updated in your audit process, right? You needed to also adapt a little bit the ASPICE to your process.
Yes,
it's not just it's both hands.
I'll tell you an example that was there. So we had a new component from the hardware provider. Everything was the same. They just updated the revision ID to a new number. If you look at the code, it's an easy fix. If revision ID equal to, you had already a bunch of numbers and you add that new number, it's 1 byte, 2 bytes change. From a safety process perspective, it had to go through a change process. The verification had to be redone. So a lot of work was involved, even in that small change, I would say. And that's to make sure that you're not impacting safety in an unknown way. I mean, the whole idea with safety is to remove unknowns. I don't want any unknown in my code. I want everything to be known. If something is failing, I want that documented so someone else could handle it.
Since this is a discussion, I might comment on the Agile thing. I'm one of the Agile pioneers in the early 2000s, but I turned away in disgust some years ago because it's Scrum and Safe is safe haven for tech dyslexics, basically. It's a meal ticket for the people that was left over when we got to actual work with extreme programming and things like that. And so I can't really, I don't even go to Agile conferences anymore. But when we started with extreme programming, it was because we were in the spin. You familiar might be with software process improvement. I'm one of the organizers. So we used Agile methods as a carrier wave for good practices. And with my background in safety critical, we could do that. But there is a risk with an Agile hamster wheel, where you kind of just make mid-managers, point-ahead bosses happy with iterative work, or sprinting even.
Yes.
And that's a huge risk when you do safety critical stuff.
Yeah.
You need to have, we had a rule of having 2 people doing anything that was in the patient's stomach. That's gone. We had that only 1/3 of each person's time was spent on actual coding. That's the economists killed. Now we have whatever that you blame waterfall for, but now it's called agile. And actually waterfall was intended to be iterative in the original papers. So iterative work, proper engineering, and we can't talk about agile anymore because it's just the people that is overhead that do agile these days.
I agree, totally agree.
But you might take away the agile hamster wheel as a risk.
Yes, it is. I had written a paper for my master's. It's available on my LinkedIn, which said why Agile will fail in multi-site, multi-cross-functional organizations. And most of the things that I wrote back then kind of are coming true. But thank you for that.
I survived.
Who hurt you and are you okay?
Okay, but yeah, thanks a lot, Naresh.